So we're going to run through a performance demo of the software. I know your programs say we're going to be doing performance testing of the test net, but we've decided to step back a little bit because we're going to be running some not normal, what I'm going to call not normal contracts to really demonstrate the throughput of the system. So we've opted to not run that against the test net. So in the interest of transparency here, we have a staging system that we use for our testing, and we have hooked up Grafana to it, so you'll be able to see the performance of the R node, but we will not be running it against the full test net today. So just a quick caveat before we get started. So I'm going to put two of the devs on the spot here. I want these guys to come up on stage. Wukash and Dom, will you come up on stage real quick? So Wukash and Dom are our two of the members of the engineering team. They work on the R space tier, which is the tuple space, which is really the heart of where all the magic happens. So this is Dom, and this is Wukash. I want to give them a round of applause because they really helped me tremendously in building all the tooling, working on the performance, and they're going to continue by the end of the presentation. We'll talk about our roadmap a little bit with respects to performance. But I wouldn't be standing here if it wasn't for these guys. So thank you very much.
No problem.
Yay. All right, so we'll just review the agenda real quickly. So the first thing we're going to do is we're going to kick off test number 1, which is the Doop contract. And while that test is running, we're going to talk about what it means to measure performance. We're going to talk about tooling, which is the guys have built, and then we'll review the results and then demonstrate the tooling, and then we'll do a token transfer test. And then we'll talk a little bit about, what's next for us. So yeah, we'll just go ahead and we'll start with kicking off the Doop contract, and we'll go from there. So I will show you folks the Doop contract here. Let's go. So test number 1 is what we're calling the Doop contract in engineering. And this contract enables us to generate what we call COM events within the system. And the measure of a transaction in our chain is a COM event, and I'll delve into that in a little bit more depth. But in essence, the contract as we run it now will generate 10,000 COM events for each execution. So Dom, if you want to go ahead and kick off that contract, and I will just really quickly show the Grafana, and then we will go into the presentation in more depth here. Thank you. Pause. Feel free to use a mic.
Two questions. Should we expect the same performance from the staging environment as in the testnet? And then the second one, what is that contract? What does it do, besides generating a lot of transactions?
This contract purely generates a lot of transactions. We are using it to test the throughput of the system. So the goal is that the testnet should perform at the same level. However, we've got a very large number of testnet computers, and the memory requirements for this contract are pretty high, and the testnet validators have only 32 gigs of memory on it, which is the reason why we're not running this contract against those nodes. Do you have the right Grafana app now? Okay, there we go. Okay, so we've just started running the Doop contract, and you can see here that we've got about 1,500 COM events per second. So we'll review the results later, and you guys can ask me some more questions about it. So, what does it mean when we talk about performance, right? At a very rudimentary level, we want to say it's fast. But performance is a lot more than that, right? There are multiple measures of performance. You have throughput, you have latency, right? And so we have to, it's really an oversimplification to say that it's just fast. We have to measure performance on a wide variety of multiple dimensions in order to really be able to say that the network is fast. You hear Greg Meredith talk about Visa level transactions and Facebook level content. in terms of the quantity of data that the system will store, and that is 100% our intention. But we're not going to get there with a silver bullet, and it's not just going to be one thing that we'll have to look at. Right? So what we're going to show you today is throughput. And throughput really is about the amount of material passing through a process, or the number of transactions that any given node could process. And our chain has a promise that we will deliver a throughput of 40,000 COM events per second across the network. So what does that actually mean? Well, it means that over the entire network, all of the different shards, you can expect a minimum throughput of 40,000 COM events per second. So let's talk about a COM event versus a transaction, right? Transactions on blockchains encompass a lot of different criteria, right? Latency from the network, transaction safety, and number of confirmations that are needed. So when we talk about a transaction, we're talking about the act of buying or selling something. And a COM event is something that happens within the tuple space of the node where a produce and a consume join. And what does that mean, right? So in Rolang, if you've attended any of the Rolang sessions, you'll know that Rolang is inherently concurrent. And that means I can have a process that's waiting in a channel for data. When the data arrives, you have a join, and then computation can proceed. That join is called a COM event, and that's what we refer to as a transaction. So in terms of COM events. Now, a transaction can also be a token transfer, right, which we'll see later today in our presentation. And a token transfer can have many, many COM events. It may not just have a single COM event. So you could have a contract, as we're demonstrating with Doop, which would look like a single transaction, because I'm running a single deploy. But on the back end, it's generating 10,000 COM events. So just trying to educate everybody that there's this subtle difference between a COM event and a transaction.
Fair to say that all COM events are atomic?
All COM events are?
Atomic.
Yes.
Okay. And transactions are not the way we're defining.
Yes, that's right. Yes. So safety versus speed. So one of the things about blockchain architecture and blockchain technology, the more nodes you have in a shard, the greater the security you have, right? But you also have to understand that it's going to be slower. And the reason for that is you've got a lot more nodes that are coming to consensus on any given transaction. Fewer nodes, you're going to have less security, and it's going to be faster, right? So you have great speeds with Visa today, but guess what? You have one validator, it's Visa. So our goal is to try to really get to Visa-level transactions, but still have more security than Visa in that you're going to have more than one validating node. It goes without saying. So measuring the performance of a network is going to have a lot of factors, right? Our goal is that when we shard the network that we will provide information to end users about the shard. So you'll have some understanding that, okay, is this a very high performance shard? Is it a more secure shard? But transaction times will take a little bit longer. So there will be a lot of heterogeneity in the R-chain network. So we'll talk a little bit about time to finalization, because I think this is a very important end user metric, right? So you're thinking COM events, they exist inside the tuple space. It's not really germane to me as an end user. I want to know how long it's going to take if I transfer money, right? If I'm transferring token from one individual to another, how long is it before I have to, before I know that that transaction is finalized? And that's really what we're talking about here, right? If I'm at point of sale and I'm swiping my credit card and I want to use cryptocurrency, that level of latency is very, very low. And so the beautiful thing is our chain is a proof of stake system. And a proof of stake looks at transaction finalization a little bit differently. There is a notion of finalized blocks, don't get me wrong. However, if I'm buying a cup of coffee and I have a validator that has $1 million of stake, if he has validated my transaction, it's probably okay, right? Because he has staked $1 million that my transaction is valid. And so that's what when we talk about clique safety, we basically are saying is what percentage of the stake in the shard has validated my transaction, right? That means they have put up their bond and they're putting their money where their mouth is that my transaction is legitimate. And so if I am transacting something, a very large transaction, like say for example in the future, I'm processing the mortgage of my house, I'm going to want a very high clique safety. So I'm going to wait a lot longer, right? And I'm going to look at the clique safety and I'm going to query multiple nodes to say, okay, what's your clique safety from my transaction? And I'm going to expect that I want a lot more. If I'm buying a cup of coffee, the vendor's going to say, okay, you know what? It's probably fine if 1 or 2 nodes have validated the transaction. I don't have to wait for what we call 6 confirmations in the traditional proof of work systems. And this is a very important distinction because you can design client applications on the R-Chain network to really use a lever to say, well, how much safety do you want in the transaction, right? Do you want to wait until finalization? Then you have to wait longer. Or are you willing to accept a lower level of clique safety because you're doing very, very, very small transactions and you want them to be extremely fast? So should we check in and talk a little bit about tooling, guys? Let's do that. Do you need access to the machine stress talker?
I wanted the slide.
Okay, it's right here.
Awesome. Okay, so we're running the tests using a tool we built. It's basically Gitling, if you know what it is. It's a framework for building stressing solutions. And there's a gRPC bridge for R-Chain in this repository. So if you want to build your own, roll your own solution, it's there, available in the R-Chain. Sorry? Oh, okay. It's in the R-Chain organization under our R-Chain perf harness. And we're providing a pretty simple script to build a Docker image that will run the harness. You can point it at a directory with contracts and just run it against any network you want. And then we publish the metrics using Prometheus and Grafana. Everything is open source, and they're available. So we're using that for this demo at the moment. Besides that, we have some automation, which Łukasz will talk about.
Yeah, just a few words about automation from me. So, who doesn't like automation? We want to do as many things automatically as possible. So, we leverage Drone for that, which is a CI/CD tool for setting up the environment for test purposes. And then we also have HuBot, which allows us to trigger benchmarks for now, because at some point we'll have this done automatically, obviously, for every pull request, so that we are able to decide whether we want this code to make it to the dev branch or not, and then in the end be released. Right. To-dos, alerting in Grafana and notifications. This is related to what I mentioned a moment ago.
So the goal is that we've built this automated performance harness that will basically take every Git hash, every commit, and it will run a battery of tests against it. And if the performance of the system doesn't go in the right direction, then the merge will be blocked, notifications will go out. This is a great way for us to trap any performance issues before they actually make it into the mainline code base and out to production. The other thing that I feel is very, very important with the performance of the system is that we be very transparent and auditable, right? So one of the reasons why all the tools are in GitHub, reason we have tools, the reason they're in GitHub, is that anyone can stand up an R-Chain network, they can get access to the tooling, and they can run the tools in their network, and they can verify our results independently, right? We're making a very bold claim about the performance of the network, and we believe that that claim needs to be independently verifiable. right? It's not, we don't want to have any smoke and mirrors here. We're being very transparent about it. So that's another reason why we have all the tooling available in GitHub for each and every person to, that's running a node and wants to independently verify the performance. They can do so if they wish. Do you want to demonstrate the tooling, guys? Let's review the results, and then we can kick off the second test. You going to do it up here? OK, sounds good. All right, so in the top right-hand corner, what you're seeing is the original deployment of the Doop contract. You'll be able to observe that we deployed to 2 nodes. Is that correct? We deployed to 2 nodes, and you'll see that now these 2 nodes having the Doop contract, they're 2 separate deploys. So what, in essence, you're seeing in this network, you're seeing 3,000 transactions per second across this network. We have 1 node that is, it's a 3-node network, correct? 5-node network. So 2 of the nodes have proposed a block. The other 3 nodes are validating that block. And so you'll see the green and the yellow are the proposing nodes. And you'll see the orange on the bottom right, that's validation taking place right now. So this is, again, like I said, this is what we call a little bit of a dysfunctional contract because its sole purpose in life is to generate COM events so we can demonstrate the throughput of the system with respects to COM events. Any questions on what we're showing here? Yes? How much RAM does it have, Dom?
Go up.
Yeah, you need to stay up here now.
Is it up? Yeah,
Yeah,
awesome. So to run this contract, and it's a little correction, it's 13 to the 5th COM events that will be produced during this contract. You will need about 17 gigs of RAM. It will use 17 gigs of RAM on each node.
You should just stay up here because you're going to demo the tooling.
If you have CPU, it will use it. As in, it's very CPU bound, so whatever CPU you give it, it will be faster going. In this particular setup, each node gets about 20 CPU cores, and it's just abusing everything.
It's using everything. Any other questions? Do you want to show me the other metrics down below?
Sorry?
No, you want to see any of the other metrics below?
Yeah, okay, so our harness gathers metrics from the Cayman exposed endpoint, and it's gathering, everything is gathered in Prometheus. So this dashboard is an example dashboard. We're trying to look at stuff directly on the network because we have access to it. So bare metal access is always quicker, easier to look at. But you can build any dashboard you want. And Prometheus is popular enough that there are ready-to-go dashboards, ready-to-go solutions. C-Advisor is great if you're running Docker. You just plop it in and have all the metrics about containers you would ever require.
Yes, another thing to note, these are Docker containers. This is not bare metal. And
Yep.
we have observed better performance on bare metal.
True.
Right, this is a single machine running 5 Docker containers and the Gitling Docker container. So what we're going to walk you through is setting up the Docker network that we use for testing. And again, all these scripts are on GitHub, so this is something any one of you can do given a machine.
And some time.
And some time, not too much time, but just a little bit of time. And then we will instantiate Gitling, and then we will run the test. Wait, you got to wait a second because it's not popping up yet here.
Nope. It is popping up, it's just not being put through.
Here it is, you're good, go.
Awesome.
Okay.
Okay, so this example is 1,024 wallets created, and we will be running transactions between them. And this particular run is 128 transactions, and I want to let it spin so we can see them on the dashboard. Transfers, yes. if it manages to pop up. And the next step would be to run the next deployment and the next deployment to go up to the 1024 transactions.
You can walk them
And
through this.
can I make it bigger?
Yeah, no, that's good. That's good. There you go.
There you go. Okay.
So what you're seeing here is the Docker container. He's starting the Docker container. It's called a perf runner. And he's running a section of contracts. So you see he's got a volume mount there. He's pointing to the row line contracts he wants to run. And then loops is the number of times it's going to loop through the contract. Sessions are the number of peers, and the ratio is the ratio of deploys to proposes. So you can really kind of scale in and out how fat you want to make your blocks. And then the hosts he's sending the transactions to,
Yep.
and the
that's
name of the
it.
network.
And that's it.
So this really enables us to test any number of contracts, any kind of block composition, to any kind of a network configuration in terms of the number of nodes. And then furthermore, when we spin up the Docker network, we can also configure the Docker containers in any which way we want. So this gives us a lot of flexibility, and we can also use this to really automate the testing that we need to do to make sure we're in a good place for performance.
Okay, so as you can see, we're deploying to host to peer 1. And the COM events are happening on peer 1 as we would expect. Now let's deploy to peer 2, because we're crazy like that. And it will take some time to continue, but it will eventually start producing COM events and then go into replay mode. And the more we deploy, the more time it will take for the network to reach consensus, because there will be multiple blocks competing for consensus. But it will do that.
It will eventually come to consensus. That's
Yes.
right. That's right.
Do you want to go back to your laptop?
I can go back to my laptop, yeah. So
Switching again.
I can continue with my presentation.
Yep.
Yeah, sounds good. While we wait for this to run.
Oh, and you can show it directly. There you go.
Any questions while we are doing the laptop switcheroo?
I can juggle.
Can you juggle?
Nope.
Yeah. One quick question.
Yes.
So since the Dockers are all on the same machine,
Yep.
should we expect different performance when the images are on different computers, and then the transaction needs to happen through the wire?
If you have, well, okay, so the question is, how do you define performance? If you include the network gap and you have a really slow network, then yes, obviously. But if you're interested in the computing of blocks and making sure they are valid, then there should be no real influence of the network. So the cost of transferring the blocks is an issue, but the blocks aren't that big, and we will make them smaller, hopefully.
So you would affect more the latency, but not the throughput.
Yep.
Okay. Thanks.
Okay, I have a question. So you said these two nodes are generating COM events, right? So what exactly are these COM events, and what do they contain? And do these COM events eventually lead to transactions?
Yes.
COM events are an atomic portion of a transaction. So in the R-chain architecture, because it's inherently concurrent, you can have a process, which we call continuation, that is waiting on input. So the continuation will sit and wait in the tuple space. When it receives the input, then computation can proceed. That is a COM event. Similarly, you can put data in the tuple space, and that data can sit and wait for a process to come and consume it. That is a COM event. So when you perform a transaction on the R-chain network, you are ultimately creating COM events. So the atomic measure in the inside of the tuple space, that is the atomic process by which computation happens. Right? Because if you think about it, when you run a computer program, what is it doing? You're either performing some kind of computation on data. So that's what we've chosen to call an atomic transaction. Make sense? Any other questions?
This particular instance, when you're transferring balances from one place to another, that's a transaction. When I send something from one address to another, that's a transaction. How many COM events in this particular case are happening in this one transaction?
Between 10 and 13. Yep, exactly. But still you need to validate them, and our goal is to make the time from production of a block, so running of a contract, to validation on the network as quick as possible.
Shorter.
Yep. For
So-
now, we have a pretty good delay.
Yeah, so in the interest of transparency here, right, so I'll be talking about the roadmap and the things that we're going to do with respect to performance by the end of this presentation. But you'll see here there's gaps, right? So there's very obvious gaps between the top and the bottom charts, right? So the bottom chart, you'll see, notably, you'll see this pink and blue down here. This is what we call a replay event, but it's being replayed by the node that did the propose, which probably doesn't need to happen. And the other thing you notice is there's this space in between here, down here, that doesn't need to happen. So the idea is the minute the block gets proposed, it should immediately go into validation, and we have to investigate as to why there is this extra latency, right? So we still have work to do, but I mean, first blush, we're very pleased with the initial performance that we're getting out of the system. It really speaks to the fact that the architecture of the R-Chain platform is solid, right? We've proved the computer science, and we've proven that Rolang works, and it's concurrent, and we can produce a lot of transactions per second. And our goal is to now fine-tune it so it's even faster. So we'll get back to the presentation if it presents. There we go. All right, so I'll talk a little bit about the roadmap. So one of the first things you have to do from a project management perspective, if you want to get something done, you got to have people focused on it. So the team is now going to be doubling down on performance. There are going to be individuals that will be focused on profiling, looking at the latency, looking at the performance, identifying hotspots, right? I showed you one small improvement where we can shorten the time between propose and the replay mode or validation, right? We're also going to be profiling the performance of different Rolang contracts. So we have to build a very large library of Rolang. So if you feel like writing some Rolang contracts, send them my way. I'll be very interested to identify if there's any performance bottlenecks and how those contracts are performing on the network, how they're performing within the matcher, within the interpreter. So many, many components go into the node, and each one of them will impact performance, right? And so it's not, getting performance better is not a silver bullet. It takes a lot of little pieces, right? A lot of little areas where you have to go look and make sure that you are not sacrificing performance in any place of your architecture. We have a single writer lock in LMDB, and so we're going to be looking at optimizing that in certain cases where the channels are disjoint. We don't need to grab a lock on it. We have some areas where we can optimize when we grab the lock, if we do it before we're processing a transaction versus after. And then I showed you that we've got some latency in proposed and show blocks. So those of you that have been working with the node have probably seen that there's takes a little too long to try to see a block. So the dev team is well aware of these issues, and we're working actively to try to solve them. So if you observe anything, file a ticket in our Jira instance. It's all over the Discord. It's a public instance, so you can log in and file an issue if you're observing something strange with the performance of the system, so we can address. I can open it for questions, and we can take a look. Yes, Kelly?
For the run of Doop, the one that is CPU intensive, it tops out at about 17 gigs. So it's prudent to at least allocate 20 if you want to run Doop 5. The transactions, the transfers, because I did a deployment of wallets one at a time in a big blob, it topped out at about 12 gigs, 12, not 20. And the execution of the transfers doesn't make the nodes use more RAM. But it's not a number. It's more of a, depends on the contract still. And we are aware of that, and we need to profile it so if it's reaching, the contract is too big, or the blocks produced are being too big, we need to figure out how to make them fit in a certain amount of RAM and not go scaling out to infinity. That's given.
How many COM events should we expect to have in a simple, let's say, token transaction?
How many? That was answered already. 10 to 13.
10 to 13.
There's a big caveat on that. If you define a very complex transactions that it makes a lot of stuff to make sure that identities match and so on and so forth, then you will have more COM events because that's more computation. But this particular transfer, which is, I think, available, is between 10 and 13 COM events.
I mean, we're talking about a programming language running on a platform. And so anyone that's written code, you know there's a good way, a highly performant way to write it, right? And a highly economical way to write it. And sometimes those two are orthogonal, right? So what's cheap may take a very long time, and what's very fast may cost a lot, right? So there's another factor in here, right, that's going to play in, is going to be how much are these transactions going to cost. And so if you're authoring contracts, another lens that DApp developers I'm sure will be looking at is how much does it cost to deploy and maintain my contract on the blockchain. Any other questions? How are we doing on time? Oh, I think we're finishing early. I don't have anything else to share unless there's something any of you want to see in particular, or any other questions you may have. I'm open. Going once, going twice.
Thank you.
Thank you very much.